acid catalyzed, not acid or base catalyzed, only acid catalyzed for Fischer esterification. And basically you do, basically it is exactly the same as trying to form a hemiacetal, sort of. Like, it starts in exactly the same way as trying to form a hemiacetal or an acetal. We take an alcohol, we're going to attack, but this time, we have a convenient leaving group, right? We've got 2 oxygens already, and so, I mean, it's definitely, nature's definitely not gonna tolerate 3 single carbon-oxygen bonds when it can just as easily kick one of those off and make a double bond that's more stable, right? So, it looks very similar to the others. Acid catalyzed esterification is reversible. So you're going to have some of the carboxylic acid and some of the alcohol remaining. I mean, it's reversible, so it hits equilibrium and then it stays at equilibrium. Luckily, ethanol is cheap, and like most alcohols, so a lot of times you just use like the alcohol that you want as the substituent or as the reactant. You just use that as your solvent, and then you're already pushing equilibrium as far as you can anyway. So you'll still probably end up with a little bit of carboxylic acid, but you know, 100% yield doesn't exist in, I want to say in chemistry, at least in organic chemistry. So just like, excuse me, the other times we have used an alcohol as nucleophile with a carbonyl, it's nucleophilic acyl substitution. Let's see, yeah, if you compare things, or if you control it, you can get high yield. And then you can remove water by azeotropic distillation and a Dean-Stark trap. That's, I don't think I have the picture in here, but I'm sure that's in your book, figure 16.1. I'm not gonna make you know that, but if you're curious, how you would get rid of water when it forms an azeotrope, and so, you know, you can't just boil it off. Azeotropic distillation. Oh, 16.1, that was chapter 16. That was the thing that was the picture, the like only picture of lab equipment that we had on slides. That's what that was. Oh, all right. They don't. What? Okay, all right, fine. Apparently, I didn't just leave this mechanism off the slides. They just don't have a mechanism for me, but like, I want you to be able to do a mechanism of Fischer esterification. So, it's very similar to other things. Let's move on and come back to this at the end to make sure we get through other things, but like, let's come back to this and probably do this anyway, just because, I mean, I don't know, mechanisms are fun. But let's at least do product prediction for Fischer esterification. What are we gonna get for this? What's the thing on here that we remove and replace with something?
Hydrogen.
Yes, what are we replacing it with?
Methyl.
Yes. Now, that's how you predict this is how we predict products, right? We're taking off the hydrogen and we're putting on the methyl. But like, when we actually think about chemistry, are we probably taking off the hydrogen and taking the methyl off of the OH and putting it on there? No, this methyl brings its oxygen with it, right? And then this guy gets protonated, is a leaving group as water, and now you've lost one of these two oxygens, and whatever was on here is now on there. So if you isotopically label like your alcohol, you're in very much excess alcohol, that would be so expensive, then you will find alcohol in there. I guess if you really want, you can just not do excess and do excess of this instead for reasons. And then if you labeled this one, all of it would end up on the ester. Let's see, on the other one, are we going to, we remove the hydrogen and we put what on there? For this guy?
Ethyl.
Ethyl. Do we do it to both sides or just one?
Would we do it both since we have excess?
Yep. Yeah, and also, like, even if you do a 1-to-1 mole ratio and you're like trying not to do excess, are you really gonna get one of these to react before the others? I mean, one, they're entirely equivalent, like it's literally symmetric, but also, I mean, we've got no reason to believe that a carboxylic acid shouldn't react, right? Or that reacting one would make the second one slower, so yeah, it would do both, there's no difference. Let's see. Formation of methyl esters using diazomethane. So we have talked about diazomethane, and we haven't really used it in, we haven't really used this in a mechanism yet, I don't think. Is that correct? I'm gonna say that's correct. So, diazomethane is a potentially explosive toxic yellow gas. Apparently we still use it because it's helpful, but like, if there's any way, it does methyl esters, and it does methyl esters really well. So if for some unknown reason, you can't use an alcohol, you can't make a methyl ester the normal way, Fischer esterification, or anything else you can think of, I think it's literally just Fischer esterification. Yeah. Then, if you really need a methyl ester, you can use this, but it's more dangerous. So, that's what it looks like. It's got this nice little resonance structure. And if you look at this, so this resonance structure is going to be our useful one for doing synthesis, right? Because it shows us, oh, okay, this is going to be, this carbon is our nucleophile, right? And it also shows us something else. That nitrogen triple bonded to nitrogen is N2 gas, right? So, yes, this is like a 2.5 bond at the moment, but like this is giving us a sneak preview of the really super stable leaving group that this is about to make, right, and kick off. So, yeah, and this, in this case, yeah, so let's do this. All sorts of mechanisms and stuff, but okay. We have yeah, that's what I thought. All right, I'm not going to color code yet. All right, we have this, and it's still like color coding, so we're gonna do so that our colors are meaningless. There. That and red for our mechanism arrows, because I don't know, why not? This guy is going to say, hey, that's a really nice hydrogen you have there. It would be a shame if somebody took it. And we just have a nice little arrow that's like, well, it doesn't really go that far. It just sort of stays on the oxygen. I mean, you could also put these here and put that there. It's just that it's drawing an extra arrow to get the same thing in the end, so chemists are inherently lazy, so I'm not going to. But like, you wouldn't be wrong if you make this form a double bond and you kick this off. So we have O minus, that's oxygen, and a little minus. And we have methyldiazonium cation. Diazomethane, methyldiazonium cation. That's how we name that. It's in your slides. I don't care. You don't have to know that. That's a fun fact. All right, so next step. I'm just gonna redraw. Like that. And we've got I'm gonna do a mechanism arrow, and oh wait, yeah, sorry, charges. Okay, mechanism arrow. You remember how we were talking about Fischer esterification, and I was like, okay, but like how do nucleophilic attack work? How do we normally do stuff with carbonyls? We're not just gonna take off the hydrogen and literally put a methyl onto there, right? That would be ridiculous. We use this guy to do that. So for Fischer esterification is like, throw some acid in there and nucleophilic attack does its thing, and that's that, right? That follows like all of our normal, it looks like half to 2/3, I wanna say 2/3 to 3/4 of the mechanisms that we've seen so far. In this case, it kinda looks like this guy has a whole lot of electron density, and like the structure of nitrogen gas. In the structure of nitrogen gas, both of them have a lone pair. So it kind of looks like this guy might have a partial positive charge because one, we can resonate this, and two, well, the really, really good leaving group is a good bring the electrons with it leaving group, right? So, this guy, it turns out, was our electrophile all along. And we do a nice attack, and we do that, and we get, because I always put these into each other, gas, and there. Move that so it doesn't look quite so connected to this, but we have this. And I didn't color code our oxygen when I went over there, mostly because I only colored one of them, and these are interchangeable. So, like this is in resonance, so there's literally no way to tell these guys apart. They really both have a 1.5 bond, and so if I'm going to do that, I should probably do that because you'll never be able to tell the difference between those two oxygens. Yeah? Weird. So when you see diazomethane, which diazomethane, I'm not going to expect you to know the structure to that. Much like a Wittig reagent, like if a Wittig reagent is like somewhat I don't know, like somewhat suggested or something, or they don't actually have the full Wittig reagent drawn out, I'll draw that for you on an exam. Like, you can ask me for that if somehow it slips my notice and you get an exam that like wants you to do Wittig, it doesn't show you the structure of it. Same with, what is it, chlorous acid for forming something. Oh, chlorous acid was used as an oxidant, right? Oxidizing agent, it oxidized. I think that's what we did. Anyway, there's one of those mechanisms with chlorous acid, and it's chlorine and like a bunch of oxygens, and you don't have to know that structure. Likewise, you don't have to know this structure. I'll give it to you, and if I forget, ask me and I'll draw it on the board during your exam. So, yay, mechanisms. We get that. Okay, acid chlorides. So, this is another thing we can do. Instead of having a carbonyl group with an OH, we can have a carbonyl group with a chloride attached to it. And, well, because we're going to talk a lot about what these can do in the next chapter, which is carboxylic acid's cousins, derivatives thereof. But, like, basically derivatives of carboxylic acid are like a carbonyl, but there's something here that can do chemistry rather than just a carbon, so you can only add, like, something here that can eventually leave and allow all sorts of chemistry to happen. So, we can make this, and we have a mechanism for making this. Acid chlorides are very, very reactive. They're not very expensive, and they're really synthetically useful for both of those reasons. They can do all sorts of useful things. All right. Let's see, what time is it? Oh, yeah, we're good. Hold on. Oh, yeah, we're totally good. We'll probably have time to do. We can either do Fisher acidification or do, I don't know what else. Substitute things. All right. So step one, we've got I think I put conversion to acid chlorides on here on your list as a mechanism that you should know. And what I didn't realize is that their first step is not a step. I mean, oh, you can't see that, sorry. They don't show our things. Okay, I guess we, see, this is multiple steps. So you don't, I will delete this from the list of things that you need to know, because it's not a useful mechanism if they skip steps. So the way that this would really happen is you'd have to deprotonate this and turn it into that, right? That's a whole step. And then you're gonna have that, probably attack that, do that. This is not happening in, it doesn't say it's, well, okay, acid chloride, so, I don't know, maybe we can leave this, and we can get, oh wait, I'm gonna draw it from, no, yeah, C-O, I guess we would have this in between here, and then this would get deprotonated, that's a plus. That would get deprotonated by something, and this would reform his thing, and kick off one of these guys, and we would get S, C, O, O. Yeah, because we have, that guy takes his electrons with it, so it's a Cl minus. This gets taken, like in taken, so it's an H plus. So, that's several steps. I hate when they do that, and they're like, this is totally a mechanism. It's like, this is like a third of a mechanism at best that they're about to show, because they do have another step here. Well, I'm just gonna unhide that slide too, why not? So basically they're like the mechanism is 2 steps. This is a bunch of steps where you don't have to know the mechanism, because if it's a mechanism, that to me means you do arrow pushing for every single step, everything that happens. You should be able to know where the electrons come from and where they go. Where do they come from, Cotton Eye Joe? Is that still like a thing that do you guys know that? Okay, I was just making sure they still played that in, I don't know, for elementary school gym class square dancing around the globe. All right, so we've got that. Give me this. And now, I'm gonna redraw that thing, and we're gonna have, now we actually have some arrow pushing that, you know, counts as a mechanistic step, unlike what we had before. So many dots. Okay. And what we kicked off is, we could write it like that, but like really HCl is a strong acid, so we've got that and that, right? So we have some of this floating around. So what can happen is this guy with all of its electrons can go, hey, what if I attacked, okay, yeah, good, there, because you look a little bit electropositive, my friend. Electrophilic, one might even say, because I don't think electropositive is a word, but the opposite of electronegative, yeah? Does that, when I say, like, I'm pretty sure I'm making that word up, and I think I've used it several times. Is it confusing, or is it like, oh, obviously it's the opposite of electronegative, like that's a useful made-up word for us? Is it the latter? Or do this if it's helpful, and this if it's like, you're making up words and that is not helpful? Okay, cool, thank you. Needed a quick poll. There's a chance I'm not making up that word, but like also, I don't know, it should be. We're gonna get an intermediate of this guy, CO minus with a chlorine there, and that, and that, and that. And this guy is all just one really elaborate, really good leaving group. Because the next step, I'm just gonna go down. I don't want to draw that again. The next step is where this goes, hey, you know what? Remember that thing where you've got 2 carbon-oxygen single bonds, and like everybody's way happier and way stabler, more stable, if we just, you leave, and I get to be a double bond, so bye. And that guy leaves. And actually, this is such a good leaving group because of all of the resonance that can happen here, because you've got, so this guy is sp2, right? It has to be, because it's a double bond. So these guys have one of their, they have a pi bond that's forming out of the p orbital that's coming out, like sticking through the board and sticking through the board, right? These guys are right next door to sp2, and they've got lone pairs. So even though Vesper theory tells us, oh, those are probably sp3, in reality, these guys have one of their lone pairs in the parallel to the other ones, the sticking out of the board p orbital, because why not have all of the resonance happening, right? Opportunity for resonance, let's do it. So really, these nice steps happen. There we go. Yeah, chloride is a good leaving group, and all sorts of things are good leaving groups. And we get Cl, the thing we wanted, and then SO2, pretty sure that's gas. Yeah, uncharged, that's gas. And more Cl minus. Yes?
Oh, what happens to the lone pair on the sulfur from like the one step? Because if it,
Oh, yeah, so sulfur breaks its octet rule with this.
oh, gas.
Yep.
Okay.
Yeah, it totally, because sulfur is, I would say sulfur's below oxygen, right? Or no,
It's right.
yeah,
below.
it's right below oxygen. So one, it's down a level to the point where we know that d orbitals are energetically accessible. We could feasibly reach them without just going, this much energy and that much energy. This is totally, we could do that. Like, these are actually energetically accessible. And the S should come with, well, it should come with 6 valence electrons, right? So usually we can count like how many bonds. Usually it's just like, oh, that means it's 2 lone pairs. But really, if we really want to do this, because it's, you know, not 2 lone pairs, but also there's not 8 total, we cut all of these in half, and we do 1, 2, 3, 4, 5, 6. So when it's bonded like this, it has no charge because its formal charge is, you know, it has all 6 valence electrons that it came to the party with. But yes, this is, I mean, even beforehand, right here, we're breaking the octet rule. And just because, yes.
I think what he was asking is from the bottom right one on that board, it doesn't have a lone pair.